Welcome everyone to JDAC's in vitro diagnostic webinar on validating and measuring centrifuged blood samples. My name is Justina Valencia and I'm part of the marketing group at JDAC North America. On the line we have our presenter, applications engineer Don Wyrick. Today's agenda will consist of a quick intro to JDAC and our presenter, a summary of how to validate and measure blood samples that have gone through centrifuge processing, how to identify sample impurities, and a step-by-step video tutorial which will walk you through a sample script that demonstrates machine vision processing. We'll conclude the webinar with a Q&A after the presentation for those of you who have any questions about today's topic. We encourage you to type in any questions you may have into the Q&A window located at the top right-hand corner of your screen during the webinar so I can read your questions to Don once he has finished his presentation. Please be sure you're typing your questions to the host. We'll do our best to answer all of your questions. However, if time runs out, we'll email you back the answers to your questions. At this moment, I'd like to request that everyone mute their lines so we can get started. So here's a little info about JDAC and why we're the expert on this topic. JDAC, which is a business unit of Novanta, specializes in machine vision, RFID, barcode, printing, and computing products, providing both off-the-shelf and optimized products for medical device manufacturers. We were the first to implement embedded machine vision solutions to medical devices such as clinical analyzers, surgical machines, assay readers, and more. Our expertise is in healthcare. In fact, about 90% of JDAC's business is with medical device manufacturers. Almost any scanner in the medical industry today, good chance it's a JDAC solution. We're the #1 leader in OEM imaging engines to glucose meters and portable analyzers, #1 market leader of OEM imaging to infusion systems, #1 supplier of OEM engines to the healthcare market, and #1 scanner used with patient monitors, ultrasounds, and infusion pumps. Now a little background on our presenter, Don. He's an applications engineer who has served JDAC for almost 18 years and has 35 years of experience in technology development and hardware and systems design. His education includes Clarkson and Syracuse universities. At this time, I'd like to turn it over to Don. Don, the floor is yours.
Thanks, Justina. I'd like to say good afternoon. However, I see that there's a number of different attendees that are coming in from all over the world, so I'll just say hello all. Let's take a look at just how do you validate and measure blood samples that have gone through centrifuge processing, and the essential answer is machine vision. Machine vision uses processing based on common and customized algorithms to inspect and analyze visible characteristics, make decisions based on absolute criterion which can be stored internally but traceable to external standards, and then deliver these findings in simple format to the host or system controller. A quick note about the environment, and this is an important aspect. Machine vision is dependent on critical aspects of the image capture and lighting environment. This is where our engineering knowledge and experience is critical. JDAC personnel regularly attend conferences to keep up to date on the latest aspects of machine vision related topics. For example, our people recently attended the AIA conference where an entire session was devoted to illumination as used in machine vision. JDAC supports all aspects of measuring and understanding the mechanical limitations in sample handling, and works to create the optimal support for a particular machine vision mission. So why pre-process, as this situation is, pre-process test tubes that have gone through centrifuge processing? Essentially, the issue is that we're pre-screening blood samples before they go into final chemical analysis. This increases the level of automation and eliminates the human intervention of pre-inspection of these samples, achieving quality and applicability to the follow-on processing. Placing this step in the overall process then results in improved throughput, consistency, accuracy, and efficiency. And again, more in the detail of how you validate and measure blood samples that have gone through centrifuge processing. The specific machine processing that we are using in this mission include shape detection, that would be cap shape, and can also include cap color, liquid level assessment, and this is basically to ascertain the level between blood cells and blood serum, and of course the test tube. These are based on transition from one color to another or one shading level to another. And then within the zones of red blood cells or serum, we are doing color detection via matching, color matching, using well-established color matching algorithms applied to match the internally stored reference colors. And then as the last step, we're going to look at the impurity level and the clarity of the sample areas. And we'll look at that a little closer on this slide. As you can see on this particular sample, we have some impurities both in the upper area on the wall and also within the serum area. The issue with these impurities is that these impurity areas, if a pipette is sent down into the tube to retrieve serum samples somewhere from the serum area, if they happen to retrieve a serum sample from an area where a clot is, it could very well throw off the results of the testing, the follow-on testing. The image processing is applied to highlight non-uniform color or non-uniform shading areas in the area of interest. In this case, we're mostly interested in defects within the serum area. The assessment of this clarity is based on image pre-processing and by the blob detection methodology. These are all demonstrated in more detail in the walkthrough demo. And so now we'll go to the walkthrough demo. This will play out on your screens in a compressed format to save bandwidth, but the recording of this session, which we will send out afterwards, will include a full screen size version of this demonstration.
Let's dig deeper then into using some of the constructs and capabilities that are offered on the Clarity scripting platform and the JDAC machine vision platforms that'll achieve our end mission of validating and measuring centrifuged blood samples. I have here a handful of representative images of some collections taken. The first step, of course, is to acquire an image. These controls down here are direct hardware controls that control the acquisition process in the camera. There's some iterative work that has to be gone through to get these settings correct for the best uniformity of picture-to-picture and the best utilization of the illumination. It should be noted that the most critical part of machine vision operation is the lighting and illumination around the object. For each of these samples, what is of interest and is the areas to be measured are the color and purity of the serum section and the color of the red blood cell section. There's also measurement being done on the total volume so that to guide machinery that's farther down in processing, then maybe inserting a needle through the top that will be pulling, needs to know the height of the serum and of the red blood cell areas because it's going to go into one or the other to pull a sample out of the test tube. I've jumped into the whole operational script now just to kind of give an overview of the uses of the different features here and the different processing here. We have the acquired image process, which I mentioned already. We are anchoring some of our processing to a feature on the test tube, so we have a pattern match process. We are finding edges, liquid levels, using a edge finding process in two places. And finally, we are looking at some color measurements in various zones, the red blood cell and the serum zone. We're going to do some measuring, basically a mathematical output of the distance between these two interfaces. And then, of course, we're going to construct the output string that will come out of the machine vision platform that this script will be loaded up into. I've backed all the steps out of my processing for the moment, and we'll build up the processing that's required as we go along here. We've already talked about the acquire image step. What I have to do next is to try and grab this feature of the cap and lock to it in order to position the rest of my processing. This will require a pattern match process. However, pattern match and a number of other processes do not operate on color. So I have to take this color picture that I have first, and I have to insert an image process step. Basically, all I'm doing with this step is I'm converting to a grayscale image. Now I can add the pattern match step. What brings up initially in a pattern match step is the picture, and now we're finding a training area. So what we're going to do is train on the edge of this cap here. We're going to use an edge match because the pixel match is just too involved with getting to exact shading from one picture to the next. Edge match is a lot more forgiving. And of course we have edge strength measurement. So we just basically want the outline of the cap here to be our guide, so we can adjust appropriately. If we take that and then work through our different pictures, you can see that some of them do not respond well enough to finding that. So we have to go through an iterative process of giving it matching score, minimum or maximum angle. This process uses this step uses the image processed picture from the previous step. Any one of these steps can use the original acquired image or can use the image processed image. I've now added a process to find the liquid level that is the interface between the red blood cells and the serum. This region of interest here was sized in order to cover the extent of what is likely to be the red blood cell interface. It's not necessarily the whole tube, because the red blood cells should never fill the whole tube. This process is anchored to the pattern match process that was previously executed. So as I go through the different samples, if the cap is off from the previous sample, the region of interest aligns itself with the cap position, so that I'm always looking at the same point, general area of the test tube as I go through and look for this level. Again, we're looking for a line. We're finding a line. We're finding a line that goes from darker to lighter. It has a reasonable distinctness. These are all parameters that experimentally are worked through here using contrast adjustment and shape and length. And of course I'm looking for the first transition, which is the blood to serum transition, so it is the leftmost transition. Now I'm adding another level determination sequence. This time I'm finding the top of the serum level. This is an important parameter for the sake of measuring the distance between these two, and also for locking the color measurement portion to some feature that is deterministic for the area that you're going to be measuring. Again, I've worked through some of the parameters that get me the most consistent performance across all of my samples. You can see. One more feature of this step is that I have anchored this process to the previous process of finding the RBC level. This makes the most sense since the RBC level will be, the serum level will be above the RBC level. From that anchor point of the RBC level, which is here, I've moved my region of interest a little above that, and I'm looking again for the leftmost transition. Again, you roll through the different samples to make sure that, that the criterion that I've listed operate well and are valid for most of my extreme variation of cases. Now we'll get into the aspect of color measurement. In this case, I want to measure the color of the blood area, red blood cell area, and I want to measure the color of the serum area. What I've done is I've put a region of interest for measurement. I've moved it off to the side a bit to avoid this area here of specular that occurs in pretty much every sample picture. The blue box that's moving along with my color sample area is the region of interest applied for my white balancing processing that adjusts the sample color to compensate for the illumination intensity or shading variation that happens across the different areas where my sample area is being taken. It's interesting to note that as we select out colors in the bottom here, this is basically the color that we're matching according to this reference chart. And you see the color that we're matching is not necessarily the color you see that you might see visually in this picture because of the action here of this adaptive white balance region and how that affects the color of the sample that's taken. This index along the side here is what's known as a color distance. It's computed by this CIEDE methodology. It shows that, as you might expect, this color, if you visually look at it, is very close to this color, also very close to this color, which is kind of indicated by the numbers here being a very close numbers. And in some cases, the color distance is quite a large distance number-wise. These color distance numbers can be output as well to give you a confidence level of how close you are to matching your reference colors that are stored. At this point, let's take a short trip to the side here and discuss how I get this reference color table loaded into the script. I'm going to take and move this white balance area to the middle of the screen for this part of the demonstration. I have here a designation box that will give me the reference color that I'm seeking. And you can see that color is over here. If it's this color, it's over here. If it's, for instance, the cap color, which is useful for programming cap detection, cap color detection, it appears over here. You can see each of these is adjusted slightly based on the reference white balance reference patch that I placed in the middle of the picture here. What's also oftentimes done is to collect a picture of a reference strip from either a bottle or a document of some kind and capture the colors off of that. Now this is a picture that was captured off of physical paper in the same fixture with the same lighting as my sample examination is done, just for consistency of lighting and color calibration. For instance, I can grab a color off of one of these strips. I can add this color, give it a name that corresponds to its value in a table or an index, and save that color to this table. I've done this before with a different set of references. As you can see, you can add all these colors in. Now let's get back to the main script. I've now added a similar process here to find the serum color. Again, the region of interest for determining the color is anchored to, in this case, the serum level. It's set to be just below the serum level. I also have my region of interest for white balancing, and it's locked to the same index as the same process output as the anchor for my measurement. As I roll through these measurements, I can see that region of interest moves along with the serum level, and also the white balance region of interest moves along as well to match the position of the sample area. For these representative samples I have, you can see that my color matching does indeed span over several of these reference colors that have been stored already. And some are drastically different based on their color distance, and some are reasonably close based on their color distance. Again, we're matching the color here to the reference color. This color here is a result of the white balance operation played against the color patch area. I've now added a simple measurement step that basically gives me the distance in pixels between two of the features that have been previously found in the pattern match processing. In this case, I'm giving you the distance between the liquid level found at the edge of the red blood cells to serum transition, and the transition that goes from serum to empty vial at the top of the serum level. Again, for each of these different samples, I'm getting a different distance number. This will be used as part of the validation of the sample because the distance of the serum has to be a minimum amount in order to be able to pull serum sample out of the test tube with a syringe or a pipette. And now the last step is added into the script here, and this is probably the culmination of all the measurements, is to output all the measurements. In this case, I can output values from any one of these steps. For instance, here I've had a text box that basically puts out a string that says RBC count. Then I add a value from find RBC color and find the color name. This basically is the name that I gave that color on the reference table. In this case, it would be the name was a particular hemoglobin value. So that's what comes out as a number. Then close that field off at the period, and then I'm also outputting that color distance from the same step as, again, a kind of a confidence level of how close of a color match was I to the reference table. I build this up with the serum count, same thing. It's basically the color name for the different guide values that were in that reference table, and a confidence level based on the color distance from the algorithm output. And then finally, I'm giving you the measurement for the serum height. That's the difference between the two different liquid levels that were found in previous steps. Now what it looks like coming out of the machine vision platform is basically a text string that's shown here. For every one of our samples, this text string values will change. So you can see the distance values, the color name, which is associated with the reference color, are all basically output as a simple text string. Again, it's important to note that once this script is loaded into a machine vision platform, that the only thing that is done by the host is to command the machine vision cycle, and the output here gives all the values that are part of the script. There's no other host part of the operation. The host is is not required to do any processing itself. Machine vision scripts such as this can be retrieved from the machine vision platform and tweaked and then reloaded or re-uploaded into the machine vision platform. One remaining aspect of validating the usability of a centrifuge blood sample is to basically find if there are any impurities in the serum area. This is a good example here of showing that sometimes we can get blood clotting or some other foreign object in the serum area, which if you were to try and pull a sample with a pipette out of this area or with a needle out of this area, you may pull in part or all of a clot, in which case that would throw the processing off by a large amount. You can see some of these samples have an issue and some of them do not have a problem. One approach for this is to measure the uniformity of the color in this area, or I should say of the shading in this area. I'm going to remove this output step here. One thing that enhances the contrast of an area is what we call a histogram equalization. So I'm going to add an image process step, and it's working from this image process, this monochrome image that was created above here. I'm going to anchor it to the serum level because I'm only interested in level that is associated with the serum area. And I'm going to measure based on the majority of the serum area. We're going to do the histogram equalization. You can see this enhances the contrast within that area. It is anchored to the serum level, so as I do this for each one of the samples, you can see it follows the serum area. Now I apply an object count to that area, and what I'm looking for are blob counting, and I'm looking for dark blobs on basically a lighter background. This is my area of processing interest. I'm going to move that into the area in the serum, the relevant area in the serum, and again I'm going to anchor this to the serum level. We're going to use adaptive thresholding for the process and work from the background. In this case, what is considered to be a passing of a count of at least one blob is actually a fail in this situation. And you can see where I don't have any discernible clots or objects that are considered to be blobs. I'm showing the step as failing, and really this is actually what you want to have. Now, when I construct my output for this step, I can basically give it a name of a pass-fail give it a name of clots or no clots. As that basically wraps up the operations of the machine vision platform using liquid level detection, color measurement, blob detection, finding features such as the cap.
So now I've opened it up to questions. I've got a couple that have come in already. One question here is that if the illumination around the tube is the same and the background color is the same, would it help to have a fixed white balance space on the background to minimize variation? The illumination around the tube is the same and the background color is the same. However, with variations on picture capture, hardware variations are variations from one time to the next for the, say, the automatic exposure algorithm that's in the camera. Slight changes in the position of the tube, if such a thing is occurring due to mechanical variation in the actual machinery. There are actually variations, and as I did mention in the presentation, I do have a white balance space that is in pretty much every step that involves color. I have one at the acquire image step. There is basically an area of interest that sets my exposure and white balance at that point. It's white balancing the entire image ahead of time based on some measurement area is actually less efficient because we're white balancing the entire 5 megapixel image. I suppose it's one time, but usually we white balance on small zones, our area of interest zones, especially considering that they may be in different places along in the image, and the lighting is not necessarily completely uniform all the way across that image, so we kind of move a white balance area along with our acquisition area so that we can properly compensate for color variation, specific area of the tube where our samples are being taken. Another question that came in is what is the smallest dot size that can be detected reliably? That's kind of depends on the samples, and that's part of the iterative process of going through the settings of the parameters. As I mentioned in that demo script, we have to play with some of the values, I guess is the best way to phrase it, to try and optimize. Sometimes if I get too low on the blob size, I now pick up minor variations like marks on the tube or something like that that aren't really relevant clots. It kind of depends on the process. You have to tune it for your process and decide what's the worst case that you can suffer, and then tune the process for those parameters. And I think that also Justina's gotten some questions too, so let me.
Yes, Don, thanks. We have 3 more questions, and anyone, please feel free if you have any questions you can go ahead and type in. Another questions we have is, how long does it take to set up the script?
Well, that's kind of what I was saying a moment ago. There's a lot of iterative back and forth with some of these parameters, and so it may take you several days across several hundreds of samples to tune your processing to get the best overall performance. There is a lot of switches and dials and knobs on each of those processes that can be changed. And somebody familiar with what each of those does can probably get through it in a shorter period of time, but to actually create a script can sometimes take quite a long time if you have a wide variation in the samples that you're working with. The more uniform the sample, of course, the quicker the design of the algorithm goes.
Thank you. Another question is, how long does the processing take in the platform?
Well, in this particular case, when we loaded this algorithm that we designed on the SC6 platform and then set it up with various different tubes, the processing was in the order of just under a second, maybe 500 to 800 milliseconds to go through the entire processing and deliver an answer. One of the parameters that you can pass back that you may have noticed on that script, one of the parameters that you can pass back is the time that particular step took. So if you find in your designing of your algorithm that there's a particular step that's taking using up your entire time budget, then perhaps there's some parameters within that step or some other tweaking that you can do to that step to shorten the processing time for that particular step.
Thank you. What happens if there is a label or barcode on the tube?
Well, there's two different situations that this is. If there's a label covering the entire outer circumference of the tube, then I think you're pretty much out of luck as far as pre-processing these samples. There have been techniques that we've been exploring and that have been researched for using infrared or laser or something to get the liquid levels passing through a label, but it does not address the situation with trying to color match. Now, if the label has a gap and it doesn't extend around the entire length of the tube, what we've done for customers is we've created a stitched image, and that's also part of the standard algorithms that we have within their machine vision platforms, is to basically take a slice of the image and concatenate these slices to form one contiguous image, flattened, so to speak, of the entire tube. Now, this obviously requires the machine to be rotating the tube as we capture this image sequence. The processing is then done on that entire overall stitched image, and for instance, most of the time we're doing a barcode interpretation for a number of them, perhaps a character interpretation for other part of the label, and then the part that you can actually see through to the contents of the test tube, we would be doing our liquid level and color processing on that segment. In practicality, there is some minimum amount of the circumference of the tube or around the outside that has to be exposed to the contents of the tube to be able to process.
Very well. I believe that concludes our Q&A portion of the webinar. At this time, I'd like to thank all of our attendees for joining the webinar today. A special thanks to our presenter, Don, for his presentation and time. A recording of the session will automatically be emailed to those who registered for the event within next week. And I'd just like to reiterate that since we did have a little technical difficulty there in the middle, that we are going to patch that up and it'll be full screen and clear for everyone to see. If any of our attendees have any further questions on machine vision or any other technologies, we invite you to visit our website, jdectech.com, or schedule a tech day with us by emailing us at techday@jdectech.com for a free technology consultation. Thanks again for attending, and have a great day.